Hi, everyone, and welcome to our webinar, Database Performance at Scale, only the good part, or at least that's the non-official name. So let me introduce myself, and Felipe, then I will switch to you. So my name is Tzach Livyatan. I'm many years in DB, like 11 years, and recently moved to the growth team and to the Boston area. And I will be happy to talk with Felipe on database performance today. Felipe, do you want to introduce yourself?
Real quick, thanks, Zach. I am a technical director at SLAs, one of the many co-authors of Database Performance at Scale, and I am basically incumbent with the task today to try to summarize the book and really discuss, as you said, Zach, the good parts of performance at scale as it relates to database. Yeah.
Thanks, Felipe. And a little bit of a housekeeping. The webinar will be recorded, so you can hear it again and again and again if you want to. And also, we'll try to make it interactive. Please use the chat to ask questions during the session. And from time to time, I will stop Felipe and read out the question. Felipe will do the major part of this session. So feel free to start adding questions in the chat right now, and we will try to answer most of them. And as Felipe mentioned, this is a follow-up to the book, Database Performance at Scale. By the way, I read it. It's a great book, a lot of excellent writer, and Felipe. No, kidding. So as Felipe mentioned, it's impossible to summarize all the chapters. Some of them are really deep technical knowledge in this webinar, but we try to touch on a few points. And I want to start with like an introduction, which at least helped me think about performance because it can be a very wide topic. And for me, I like to use the analogy of a road system to performance, in a sense that there are many metrics you can talk about when measuring performance. So the most basic thing, usually when you talk about a database or any distributed system performance, like streaming or whatever, is first thinking about the performance as composed of two main elements, throughput and latency. Throughput, you can think about it as the number of car per hour or the number of requests per second in the case of a database. You can think about naively on one lane or more, I guess, realistic on at least two lanes. One of them can be the read throughput, the write throughput. Most databases have very different characteristic around each of them, or each performance of each. For example, in SLADB, write is slightly faster than read. On DynamoDB, it's the other way around in most cases. Each database is slightly different. And often, and this is a follow-up to the P99 conference, you want to think not about just the average latency, rather on the worst percentage of the latency. By the way, anyone from the attendant who attended P91 as well, please let us know in the chat.
Well, we hope they correct you, right? You said P91, P99.
Yeah. Thanks. Okay, so that was the most like basic. It's not naive. It's very useful to look at throughput and latency, but when you look in a distributed system, there are more parameter. One parameter you can think of is like in the road, you have maybe multiple lane in each direction, and usually or often you have a preferred road. For example, for emergency vehicle. So in database, you can think about it as different workload. And you sometimes want to allocate different priority to each workload. So for example, if there is a real-time request, you want to give it like high priority. Analytic request, maybe you want to give it low priority, but depending on the use case, it might be the other way around. So when you're talking about performance, performance of what? Performance of the real-time, performance of the analytic, performance of other operation. So each of those should be measured differently. And of course, that's add a lot of dimension to performance measurement. And last but not least, and this is something that at least in SLADB we very much focus on, often you want to extend the road. So if you are a driver, I guess you're familiar with the fact that when you change lane or there are construction on the road, there is a lot of blockage and ride get mass worse. It's often happen in database on distributed system. You want to scale out, you want to add lanes, if you will. But during this operation itself of adding a node can be very heavy in terms of I/O and network and CPU. So you actually slow down the entire system to add a node. So another aspect of performance that we are focused on is how much time it scale, but not just how much time to scale from 3 nodes to 4 nodes, for example. I want to measure the performance of latency and throughput while I'm scaling. So it's like two different parameters. How much time it take me to scale? How do I affect the current traffic or the current request per second and the latency while I'm scaling? And preferably I want to scale very fast. I want to scale out and in sometime multiple time per day. Because very often the workload like change heavily during the day and I want to scale to match that. On some roads, there is and this picture represented, you can actually change lane during the day. So that will be the equivalent of scaling out and in, at least in one direction. And by that, I want to switch to Felipe. And again, feel free to ask questions on the chat while we talk.
Yeah. Thanks, Zach. And yes, just to continue from where you've left off with your road analogy, I think context is definitely paramount when we talk about performance, and we did discuss that quite extensively in the book. Primarily because different workloads, they come with different characteristics, each with different performance expectations. And yeah, I mean, I think we will basically be monitoring chat, and keep in mind, guys, for today's event, the best questions on chat, we are really going to give you away a free book copy, which Zach and I are going to select after the event ends. So we really want to drive the conversation today according to your experiences, so we can really make it a pleasant experience for you. So yeah, I mean, database performance at scale, the book, really provides an holistic view where we are very open about the trade-offs involved when you decide to optimize things, when you decide to optimize one dimension, for example, writes or reduce the latency of your reads. And this is very similar to the run conjecture. I don't know if you guys are familiar with the run conjecture, but it's basically this conjecture which addresses the trade-offs involved when we talk about optimizing reads or optimizing for writes or optimizing for disk space. And like the conjecture, one of the main takeaways from the book is that you need to pick your battles wisely because you cannot have it all. Even though we wanted to, we want always the fastest system, the less expensive system, and the most available system. But oftentimes you cannot have the best of all dimensions you really want. And to illustrate that concept, one of the real world examples present in the book that I brought for us to discuss here today is really the Discord optimized disks, which the link is here. You are going to find in chat the link to their blog. But the TLDR is that they came up with their own setup, their own disk setup to favor data redundancy and low latency reads at the expense of write latencies. And they explained their reasons for that quite extensively and quite openly on their blog, and they were just fine about the trade-offs. So let's now look into the multiple factors that really involve database performance. And the way I structured this talk is that first, we will discuss the core components and optimization strategies you could apply within a single node, because database performance at scale, even though it was a book written by ScyllaDB, it's not just about ScyllaDB. We have contents about MongoDB, Postgres, DynamoDB, caches, and so on and so forth. And because we know that lots of people use Postgres, it's quite important for us to discuss also the multiple aspects that involve that could be applied within a single node. And then the next, as we head to other sections, we will start introducing and discussing other aspects and optimization strategies that drive distributed systems performance. And finally, at the end, we will discuss some optimization strategies, if there's time, because as you guys can imagine, summarizing an entire book within an hour is quite a challenging task. So, starting with latency, and before we dig into actual optimizations, I think one of the main lessons we covered around the book is to remember that latency is actually a compound metric, which is why end-to-end observability around your stack is really important. It is quite inevitable that the more components you have on your stack will end up adding and affecting latency. So simplifying and consolidating deployments really help with avoiding data movement, which often works best when you want to optimize for latency specifically. And what I'm saying may sound obvious, but in reality, we have seen actually many times, we have seen many situations where users would report high latency on their end. And then when we would go to their database, we said, well, your database latencies are quite idle. And again, just ties back to that idea that people always blame the database when things are slow. When in reality, whenever you have a data pipeline with multiple components involved, the failure or the slow performance of one of those components can easily hinder down your entire processing stack. So,
Felipe, can I ask you something? Sorry for jumping in.
sure.
So Scylla and many other databases have their own metrics to report about performance and latency. So what is a recommended way to like monitor performance? Look at the database metrics, or look at the driver metrics, or the application metrics, or what is like the correct way to do it?
It's really a holistic view, right? I mean, if you look alone into the database, you will be blind because you won't be able to know what is the real latency your users are observing, because your application has its own, introduces its own overhead, right? So what most organizations do that I've worked with, they often have telemetry on their application side of things, and they also monitor the database latencies. So, for example, one aspect that happens quite often that we discussed in the book is if your client-side latency becomes your tail latencies are high, but your database latencies are low, it means you have an inefficiency either on your code or on your client side. However, when both your database latency and your client's latency spike around at the same time, then it means that, yeah, the problem is very likely your database because your database latency increased as a result of whatever happened in your system. Make sense?
Yeah, so basically you need both. I
Yeah.
guess that's like, okay, thanks.
Yeah, pretty much. And back to what I was discussing, a more recent example I can relate to uh, was this situation where a team of engineers, and it's also related to your question, Zach. I was working really recently, like less than a month ago. I was working with this team of engineers where they reported to me that, hey, we we observed that ingesting a Parquet file to ScyllaDB is taking a very long time. That was their problem. And then I asked for their code and a simple, reproducer for me to review. And it was basically an inefficient loop in their application code that was slowing down their entire file processing. So I just fixed the loop and done. I mean, now it's pretty much real-time latencies. When we talk about latencies, we also need to know when you have to stop actually worrying about latency. And this is of course very use case specific. Uh, if you work with workloads like real-time bidding, those workloads often demand things like 1 or 2 milliseconds at worst for the P99. But user-facing transactional traffic can often afford longer tails. And previously, a talk from P99 from Square shared this study uh, saying that humans take roughly 69 milliseconds to perceive some delay. So if you are P99, if your application really works with humans and their perception of latency, oftentimes if your latency is below 69 milliseconds, things will be just fine. And last but no less important, somewhat also related to your question, Zach, there's this awesome talk from Gil Tene called Misery Metrics and Consequences, where he explains why focusing just on latency is actually can be a nice way to hide from reality. And this talk from Gil is one where he explained why other metrics like timeouts, hit rise, abandonment are really important KPIs you have to measure because those are things businesses and business owners care the most and can directly relate and connect to revenue generation. You can really imagine how this goes, right? I mean, if someone says, "Hey, my latency is too high," what does that mean from a business perspective? Instead, if you say users are no longer adding items to their shopping cart, that's a problem. That's a real revenue problem. So yeah. So in general, when we talk about optimizing latency, there are a few set of tricks as we drill down to individual infrastructure components, particularly involving a database, but not just a database. If you're running the cloud, for example, you may want to prefer instances that provide guaranteed bandwidth allocation. As otherwise, and we learned this the hard way, the cloud may throttle your traffic. And networking is particularly an interesting subject because your workload alone oftentimes won't be able to fully saturate your available network bandwidth. Because workloads, they are more likely to saturate CPU when they are OLTP, transactional workloads. They will typically saturate CPU first or disk IO first when they are very scan heavy or analytic sorts of workloads. But what happens is that databases, they don't just service your traffic. Behind the scenes, as you know, there are things like data replication, backups, repairs, data rebalancing, lots of streaming when you perform scaling operations that may end up consuming a very high network bandwidth and could end up hurting your traffic if the cloud throttles your network allocation, which is why you want to ensure your VMs, your the nodes where their database are running, never really get throttled. Um,
So
another,
Felipe, quick question on that, and then it's a question I got from users as well. I'm looking at, for example, ScyllaDB VM on production, and I'm seeing the CPU on 100%.
Mhm.
Is that by itself a good trigger for me to scale the cluster? Does it reflect that Scylla is overloaded, or will it mitigate, or I don't know, over time?
So that's actually a very good question. We can spend probably half an hour just answering this question if you'd like. For ScyllaDB specifically, no, because of our architecture, right? So ScyllaDB, so for ScyllaDB specifically, we follow this shard per core architecture. And what happens is that we basically allocate one thread per CPU core, and each of those threads, they run like in a busy loop, which is constantly pulling for work. For each of those threads, we call a reactor. And this reactor, it is really CPU intensive. It consumes lots of CPU cycles, meaning that when you use traditional Linux tools like top or htop, whichever favorite performance tool you prefer to use to monitor performance, you will always see that your CPUs are going to be spinning like at 100%, like nonstop. This is not a problem because ScyllaDB have actually other metrics that it uses to tell whether your CPU is fully saturated or not. 100% CPU utilization for ScyllaDB, therefore, only means that it's constantly pulling for the work like nonstop. For other databases, not ScyllaDB, oftentimes having your CPU utilization beyond 70% is problematic. And just happens because there's actually a very good article from Pavel Emelianov where he talks about how gauges work. And there is also one very good blog from Brendan Gregg, which he also shed some light on why you typically want to ensure that your CPU utilization is never past 70%. Because oftentimes, if you see it's your utilization at 70%, it's actually probably spiking to 100%, like, but you cannot see it due
Yeah.
to the way load average works. Is that a good answer?
Yes, and there is a follow-up question in the chat
Mm-hmm.
asking about comparing a Postgres vacuum operation, which can be very heavy, to ScyllaDB. I'm not a Postgres expert, but
Mm-hmm.
anyway, but I can comment on ScyllaDB that we are actively measuring the effect of day two operation or operation in general. In ScyllaDB, there is a few of them. There is Compaction, which is running all the time in low priority, but there is also a recurrent operation like repair, backup, adding a node, removing a node, scaling, scaling out. Each of these operations can consume resources, CPU, storage, network. So during our test, we are actively tracking all of them and making sure that the P99 latency of the real-time operation never exceed a low number of milliseconds, like 5 milliseconds in the worst case. And if it does, we, at least in my case, I open a bug and the dev team try to fix it.
Yeah.
So I hope that's answer the question.
Yeah, yeah. Another thing related to that question as well as a follow-up, Zach, is also the concept of schedulers, right? We have so in ScyllaDB, uh, I don't know if Postgres has anything similar, but we basically have this user space and I/O scheduler which prioritize tasks according to a given quota. So, for example, compaction often have a very low priority to the system, meaning that if we needed to run compaction and the user workload is running in parallel, the user workload I/O, IOPS, and CPU utilization is going to be prioritized over compaction. What often happens in a workload is that workloads they do not follow a straight line, a sustained throughput. Often they, over time they fluctuate. So as compaction eventually builds a backlog and the workload traffic starts to ramp down, ScyllaDB will automatically adjust its internal controllers to speed up the pace of compactions. And this is done through several other internal tests like streaming, repairs, and so on and so forth. Uh, okay, so really, we discussed about CPU and many things, but just to close here on networking, two other things you want to be mindful besides allocating instances with guaranteed network availability. If you have a cross-region deployment and your goal is to optimize for low latency, never block for cross-region requests. And there is this chart down below here from CloudPing where you can see easily that a request going from US61 to US62 or alone would take 72 milliseconds. So if your deployment require multi-region, you should never block across multi-region requests, just to do asynchronous replication and be happy. And the second thing, which really goes to tuning performance in particular, and goes back to your question, Zach, this is something we implement at ScyllaDB as well, which is this concept of pinning network hierarchies to specific CPU cores so we can isolate these CPUs from user space processing. And the reason is because interrupts can introduce CPU stalls, which are detrimental to tail latencies. And because transactional or LHP workloads can get very throughput intensive, when I say throughput intensive, I mean really packets per second, we simply isolate those IRQs to their own CPU cores. Okay. Um, so next we have disks, and really when we talk about disks, if you really want low latency, you should just use locally attached NVMEs in a shared nothing manner. Each database node has access to its own NVMEs, and they are great for costs. They are less expensive than network block storage, as traditionally available in clouds, for example, AWS CBS or GCP persistent disks. And NVMEs also allow your database to fully exploit features like I/O U-ring and techniques like asynchronous direct I/O performance. I don't know if you guys have recently been reading the news around Postgres 18. They recently introduced support for direct I/O, asynchronous I/O, and boom, they got a nice performance boost. And this is pretty much how we deploy our clusters in our cloud. Is ScyllaDB the only database using NVMe as a managed service? No, it is also the same strategy used by other database vendors like PlanetScale. And the latency chart I'm showing here is really the difference in latency they've got simply by switching disks. So
Yeah.
if you're struggling with performance in your database latency side, try switching your disks and use. We expect to see like a drop like this.
Yeah,
Sorry.
Felipe, I do want to mention that EBS have advantage and disadvantage. So the advantage of EBS that they provide higher durability and availability,
Yeah.
but of course on the expense of performance. For ScyllaDB, it's less relevant because ScyllaDB replicate the data in the database level. So it keeps 3 replicas per data center, as other databases do. But if you're using a database which does not have this replication out of the box, and you maybe don't care as much about latency, it's your SLA is higher, then using EBS might be a good choice for you.
Yeah. Yeah. No, quite definitely. It's always a trade-off. Inclusive of that Discord history I introduced earlier. They decided to use persistent disks, right, along with NVMe. So they accepted the fact that writes would be slower. So now, I don't want to really spend too much time on this. I mean, on the database internals, what makes LSM trees more efficient for writes versus databases which follow a B-tree storage engine. But oftentimes, it's a good idea to try to understand uh, that first multiple databases exist and different databases exist to sort out a different sort of problem, right? So ScyllaDB, Google Bigtable, RocksDB, for example, they basically implement as part of their storage engine is implemented on top of LSM tree, which is really this append-only data structure that optimizes very high ingestion rates. In contrast, other databases like DynamoDB and most relational ones, MariaDB, MySQL, Postgres, they often follow a B-tree engine. And the problem with the B-tree engine, specifically with regards to high ingestion, is that each write, each update, each delete that you do against your database requires an in-place update. So random IO is quite intensive when you use those sorts of databases, which is not often the case with ScyllaDB and Google Bigtable, RocksDB, and others. So next we have memory and compute, where you will typically want to ensure you have enough capacity to satisfy your SLAs. The more memory you have, the more room you have for caching, which is pretty much exploited by every database out there in a way. Be it either databases using the Linux page cache to provide some level of caching to your workload, or specialized ones like what we do here at ScyllaDB. And this is actually very interesting because ScyllaDB alone, we do implement our own caching layer, right? And one of the things we often say here at ScyllaDB is if you're placing a cache in front of your database to improve database performance, you are doing it wrong. And the reason for that is because since I explained it earlier, because latency is a compound, unless you can guarantee that almost 100% of your queries actually hit your cache, the ones which actually miss your cache will inevitably have added latency. So let's say you have 1% of your cache queries which result in a cache miss. That means your P99 is going to be worse if you actually simply queried your database directly without going to the cache. Um, this is not really a bad advertisement for caches. So caches are great tools to, protect your infrastructure, load the data faster, store the results of long-running computations. But they are really a bad component you should be using to improve database performance. And one example I discussed with both Alan Kassendorf earlier this year. Alan Kassendorf is the main cache maintainer, and Pekka Einberg, the author of the Latency book, uh, is how bad practice it is to store, for example, user sessions on your cache. And the reason why is if you have evictions on your cache and you are storing your user sessions on it, if your cache goes cold, congratulations, you just logged out your users from your application, which is a worse experience than reporting shiny P99s. Imagine how terrible it would be you navigating to a website and all of a sudden you are logged off. Your latency is probably great because cache latency, they are made to be fast, but the user experience is terrible. So yeah, be really mindful of where and how you're using a cache.
Yeah, there is
And
a saying, Felipe, known saying that there are two hard fields in computer science. One of them is cache invalidation. The
yeah.
other one is for another talk. And I do want to mention that synchronizing the cache and the database is not trivial. So the database might have like TTL or deletes or all kind of mechanism which is hard to propagate to the cache. You can, of course, it is possible, but it's not as easy as it seems.
Yeah. And for the second part, I never forgot a joke you told me on time, Zach, that if engineers were to name things, sushi would be called cold dead fish. Yeah. So real quick, so we can get past memory and compute. Uh, because memory is so important for databases, you should also be mindful of how much data you're storing per gigabyte of RAM as you give it to your database. If you want to read through 1 terabyte of data with just 1 gigabyte of RAM, there are very high chances that you will just crash out of memory. I mean, it's physics, right? CPU-wise, you also want to ensure you have enough CPU cores to satisfy your throughput, as well as, the database internal operations like the vacuum, Postgres vacuum example. So quite notably, it's impossible for you to hit 1 million operations per second with just a single CPU core. So that's why things like sizing databases do exist. Uh, However, it could happen that some databases may be unable to fully exploit the underlying hardware you throw at them. And this is an important aspect because pay attention to this because it's a direct connection to the next slide. In the right-hand side, we show the throughput improvement that Benchant got after they scaled a small MongoDB cluster to a larger deployment. They expected a 60% performance gain, but they really only observed it halfway through it. So let me see the questions before you actually talk here about vertical scaling. Can you please explain the user experience part, how caching impacts that? Yeah, so in the example I gave, and this is a very common pattern that we will find out there in the wild, if you are storing things like user sessions, cookies, for example, in your cache, and your cache goes cold or it starts evicting items, your user will be logged out. From your metrics perspective, your P99 is going to be beautiful, but from the user experience, he has been logged out. Logged out. So you say you should be very mindful of when you use caches. We have a question maybe for you, Tzach. Does
Yeah.
SLAB has use case for data warehousing? Can it be used to process large volumes of historical data?
So I would say it this way. If still a sweet spot is either real-time request or combination of analytic and real-time, because there is a unique feature called workload prioritization that allow you to control the bandwidth of analytics versus real-time. But if your entire use case is just analytics, then Scylla might not be a good choice for you. There are other columnar databases that are specialized in analytics like Snowflakes and other. And the difference there that most of the requests are ad hoc. So a BI person is sitting writing some kind of query, and every time the query is different. There is no repetition or very little repetition. That's one property of analytics. A second property that the real-time latency is not as important. It is important, but not as. So if you get, instead of 1 millisecond, you get 100 milliseconds for your query, not too bad. But on the real-time domain, where Scylla is shining, you don't want to go above 1 millisecond ever. So it's slightly two different use cases. And if your use case is just analytics, probably you can find better solutions.
Yeah, if you require lots of ad hoc querying, we are probably not the best database for that. We are mostly for OLTP transactional workloads, right? Yeah. But moving forward, let's talk about vertical scaling, because this is something that's also very something that we do here at ScyllaDB. We highly recommend that you scale up before you scale out for a multitude of reasons. First, because of the ScyllaDB architecture decisions, which I already spoke, we have our own caching layer. We have a thread per core architecture, which we name it shard per core. We have our user space schedulers. Because of all those unique architectural decisions that ScyllaDB implemented, we are able to guarantee linear scaling performance as you increase, as you scale up, no matter the number of CPUs or memory you allocate to a node. There are other benefits to actually scaling vertically before you scale out. First one is because due to mean time before failure. Larger nodes or smaller nodes, they pretty much have the very same failure rate. So here in this slide on the right-hand side, I brought to you the mean time before failure of hard drives, disks, and you can see that pretty much most drives here have a very considerable annual failure rate. And because nodes, larger or smaller nodes fail at pretty much the same rate, you would rather have fewer nodes, so you would have less failures across your infrastructure. Another important consideration to using larger instances is that it allows you to hit less noise neighbors. The larger your deployment becomes, there are fewer chances that other tenants will be sharing the same VMs along with you. In fact, in cloud, AWS, I think Azure as well, they can even provide you metal, direct bare metal machines for you. So in which case it would be guaranteed that there are zero noise neighbors. And because and all of this at the end of the day really culminates into easier management, right? No one wants to manage a fleet of 200, 500 servers if you could just, I don't know, consolidate that within just, I don't know, 9 nodes or so. But again, back to the Mongo example here. Uh, so long your database can scale vertically, you should prefer that before scaling out. So now, Zach, I would like to really pass the ball to you because you spoke previously on your intro about elasticity and how it's important. Can you talk a bit about the challenges we've seen with traditional database scaling and what we do
Yeah.
interestingly at ScyllaDB? Yeah.
I would even say challenges we had in ScyllaDB itself around
Yeah.
scaling and how we attack them. So many of our customer, and I think it's typical, it doesn't have like a flat line kind of usage. The usage fluctuates during the day or during the week. For example, a few of our customer is following a cricket game in the Indian League or NFL games or other games. So to control that, they want to scale in advance and scale right after. So in previous version of Scylla, scaling was pretty slow. So to be on the safe side, customer actually scale out the system days or sometimes even a week before the event. For example, a week before Black Friday. And the limitation was that once you add a new node to the system, first, the entire data need to be balanced. So it's include a lot of data streaming between nodes. And only that, after the cluster is balanced, then the new nodes start to serve and request. In latest version of Scylla, we have a feature called tablets. We won't deep dive into it. But with tablets, after the one first chunk of a table we call tablet move to the new node automatically start to serve request. So yes, it still take time to balance the entire cluster, but started to serve request is very fast. And of course, when you scale out, you do want to start serving request fast. The same feature with a few more property in Scylla Cloud, we call it X Cloud. So if you go to Scylla Cloud and see the X Cloud sign, it's basically mean that under the hood, we're using tablet for scaling, and you can set a flexible scaling policy, scaling fast out and in after, because you don't want to pay for the extra hardware after the game is over, basically, or the Black Friday is over, or what's not.
Yeah. And this also gives us some nice properties, right? Zach, about, for example, we are able to better utilize the storage. Can you
Yeah,
talk a bit about that?
that's correct. That's very much related to what you mentioned earlier about big node versus smaller node. With xCloud, we can actually mix and match different sizes of node in the same cluster. So we can better, like in a more granular way, fit the actual storage and compute that you need. And by that, we can achieve higher utilization of the hardware. So if previously there are like threshold was 70% of the storage and we automatically scale after that, using faster scaling and mixed cluster size, we can increase the threshold to 90% because we know that we can scale in time even when we only have 10% storage left.
Yeah. And yeah, let's talk a bit about adaptability and cost control because I think at the end of the day, for a business, this is what tablets really culminates to, right? It's really the ability to allow your database to scale alongside your workload while allowing you to pay for the actual amount of traffic as you need. Is this understanding correct, Zach?
Yes, this is more like from the pricing perspective, which is very important because usually you don't talk about performance as a one parameter. You talk about performance slash price
Yeah,
or per price because naively, if you want more performance, you can just add more and more nodes to your system. But of course, when you take price into the or cost into the equation, you want to maximize your performance per cost. And one of the way to do that is to have, and by the way, this is not unique to Scylla. other platform like EC2 offer that as well. You have different price categories. So you can reserve resources in advance and then pay less for them, or you can consume them on demand and then you pay a little bit more for them because it's unplanned. And latest version of Scylla, you can do both. So you can reserve like a basic setup of, for example, 6 node. And if you go above it, you don't have to pay the full on-demand price. Rather, we give you what we call a flex price, which is like still flexible, but you can pay for it in advance.
Yeah. And I mean, what I like about it is that, I mean, when we talk about performance, I mean, if you want the lowest latency, you could always, I would just add money to it, throw money at it, and then your performance problems are solved. But then you are probably going to pick a fight with your CFO, which you probably don't want. So yeah, I think the whole idea of xCloud tablets is to really be mindful of prioritizing performance while still keeping you within a budget.
Yeah, by
I
the
like
way,
it
I
very
mentioned earlier in my initial road system analogy that you have like throughput and latency. Usually what I see in organization, the throughput is more concern for the CFO. Why is that? Because you can easily fix throughput with more machines.
well.
So my system doesn't support the throughput. Okay, I'm throwing a few more machines to the cluster and it might solve the problem. Not in all cases, but in many cases. Latency is more of a concern for the product managers because latency is harder to fix. Sometimes adding machine just add to the latency. And latency also correlates immediately to the user experience. And these are things that UX people and product manager care a lot about. If you have one request to the application that translate, for example, to 10 or 20 database requests, even one slow request to the database can slow down the entire UX. Of course, in gaming and other application, it's critical. But by
But
the way, Pepe, we have something like 5 more minutes, and you have like 100 slides left. Just FYI.
oh yeah, I mean, yeah, quite definitely. By the way, in the book, we published the book before tablet, so we should invite you to, the second edition of it, so you can talk about tablets. But yeah, let's quickly talk about the distributed systems performance, what really matters. So uh, when you are really planning to scale your database, you should really build your system being mindful that failures are normal. And you should really decide upfront how you want to react to them, to those failures. For example, just recently we saw what happened with AWS, right? When they had their DynamoDB or DNS outage in US East 1. And you should really have a plan when it happens. Some might plan, well, accept the outage, simple enough, or switch to a different region and double your costs, operational costs, or figure out alternatives like kill switches to minimize the impact. Uh, when we talk about the not so extreme example of a full region failure, most distributed databases really span, multiple availability zones. So when you are doing capacity planning, you always want to ensure that your replicas can sustain the traffic as if you had lost one AZ. For example, one third of your processing capacity. And the secret here is quite simple. No system can sustain unlimited concurrency, and you cannot scale throughput indefinitely unless you have unlimited money. Uh, and this is quite different from short-lived bursts that databases can absorb excess requests for a small period of time, as you can see down here. But if this is not your case for your particular workload, that is, you either want to survive a full availability zone loss or to scale your cluster to sustain large spikes of traffic in spans of seconds, then you often don't have too much of a choice but to be over provisioned. Not lots of over provisioning, but you always want to have some headroom so that your database can, support scaling operations and lots of data streaming while still servicing your requests under acceptable low latency. And if you really can't afford being over provisioned, even if slightly, because that's typically the first reaction users will have, because they say, "Oh, I am over provisioned. This is not good for costs." Yeah, it's not. Then what you have to do is you queue your requests elsewhere in your application, uh, which means you will add latency to your users anyway, rather than throwing the excess work to your database in the hopes that it will magically solve the problem for you in case you have a major failure. Um, I think we can skip that slide. This is the one where we spoke about you spoke about workload prioritization, right, Zach?
Yes, yes, let's keep it in the essence of time.
Yeah. Um, so on this slide, I also don't want to spend too much time on it, but mostly to conclude this section. Uh, Multiple databases have different implement different strategies on how they will replicate data. So for the Postgres users here in the talk, you probably are familiar with the single leader approach, where you have a leader replica which accepts writes, and the follower replicas only accept reads. This is also the approach used by MongoDB. When you want to scale this setup to a multi-region, you go multi-leader, which introduces lots of data reconciliation quirks, which you must be aware of. But the problem with both of those approaches is that scaling right is really hard because you can say you always have a single leader that's always responsible for handling your writes. So if the single leader becomes saturated, you have no choice but to eventually introduce sharding to your database. And then databases like ScyllaDB, DynamoDB, Bigtable, and others, we really follow this leaderless approach, which allows multiple nodes, multiple replicas in your cluster to accept writes, which is yet another reason why those databases are preferred when we talk about scaling writes. For very high ingestion workloads, you typically want a database that has a lock-free pattern. And of course, as I previously mentioned, scaling it starts with sharding, right? So whenever you are plan to add sharding to your database, this requires a mindset change. So whenever we talk about the normalizing data, this really means storing data the way you want to read it. This is what the normalization from a relational model means. Because you want to minimize the amount of work your database has to do and the amount of internode communication for it to be able to retrieve the data you're after. It also means designing for predictability and whenever possible, it's not always possible, especially if you're in a financial institution, to embrace eventual consistency. So as Zach said, I do have some other slides on how to optimize latency. You will receive the slides after the talk. They are all contain blog posts about how to implement each strategy. So, for example, coalescing is a technique Discord uses to reduce the amount of requests they drive to the database. How you should be driving network latency on a distributed system instead of routing batches against a single node. Prefer individual asynchronous requests so you can fully maximize your cluster processing power. And then I give an example on how you can make seemingly strongly consistent use case, transform a stronger consistent use case to an eventually consistent one with a few application logic chains. And I give some Golang app example for you. That's what I had to present. Zach, would you mind talking
Thank,
about our upcoming events? Yeah.
thanks, Felipe. And by the way, the book is available in a soft copy on the website. There is a link Cynthia published earlier. You can scroll up and find it. And there is also a recording of a masterclass that Pekka and Felipe did. Both are recommended. Yeah, thanks for the link. Again, the book is recommended, and we have a few events that might be interest to you. Next week, November 12th, we have a ScyllaDB University Live. It's a free training courses for new Scylla users. We have a basic track, advanced track. I will be there. I will be on the advanced track talking about Scylla as a feature store. We're going to cover vector search, another topic on the advanced track. Felipe will be on vacation, I think. So good for you, Felipe.
Yes. Thank
See
you.
you on the next event. And we have later in 2026, we have the Monster Scale Summit, which is like 2 full days about Scylla. And of course, everyone is welcome to go to Scylla Cloud and try Scylla for yourself.
Yeah, I see we have one question in QA. Does ScyllaDB have a caching layer? Yes. And how do you handle caching validation? One of the hardest things in computer science, Zach. Would you like to address that, Zach, or I can?
Yeah, first, I'm not saying the same question that you are. This is kind of
Yeah, I'm
strange.
saying on QA. QA.
On the
Yeah.
QA, not in the chat. Okay, yeah.
Yeah.
The cache invalidation, we do keep Scylla do keep a cache, but it's like ballooning. Scylla can shrink down the cache or extend it based on required memory. One thing that related to performance and cache, you can control in Scylla if you want a specific query to populate the cache or not. One of a mistake, this is not just unique for Scylla, but a mistake you can do is, for example, scan a lot of data sequentially. Let's say you need to scan 1 billion records from a database, do something, some analytics. You usually don't want to populate the cache with these records because every record is going to the database, to the cache, going out, going in, going out. So you are wasting a lot of effort and basically wasting your entire hot a record in the cache for a full scan. So in Scylla, for each workload, you can specify I want to use the cache or bypass the cache. So that's a good trick you probably need to consider. There was a question, last question probably for today about lightweight transaction. Plan to extend lightweight transaction to multiple partition and table. So yes,
Good
we are
question.
planning to do that. I don't want to give like a timetable for that, but one of our major theme for next year, 2026, will be to use the Raft protocol that we are already using for metadata like schema and topology to extend that for data as well. And improving the performance of lightweight transaction and extending it is one of the first thing we're going to do.
Yeah, and as Cynthia said, attend Monster Scale Summit if you'd like to know more about
For
roadmap or
sure.
ask more questions about Scylla. With all that said, Zach, I would like to give you and our audience a few minutes back. Here's another last invite to Scylla Universal Live. I will be on vacation, but Zach himself will be there presenting about vector search. Yet, I mean, we haven't really spoke about vector search here today. That's yet another aspect that is driving lots of database performance and
Yeah.
considerations. Maybe for a second edition of the book, who knows? But yeah, with all that said, folks, if you're interested in learning about xCloud, vector search, and or even more about ScyllaDB, please attend Scylla University Live. And with all that said, folks, thanks for joining us today. Stay in touch and see you shortly. Bye.
Thanks, everyone.